So we lost in this series.
All right, folks. Thank you. And welcome everyone to Land, Water, and Climate Modeling. I'm Sonali McDermott, and I have been tasked with shepherding this session to success, which means that we're on time, 15-minute talks. I will be giving an alarm at 15 minutes. And I think the way that we'll work this is hopefully we'll have time for at least a question, if not a couple, by the end of the talk. And then we can have a discussion that's a bit more complete. So if you can't get your question in, just hold it and we'll hopefully return to that at the end of the session. Does that sound good? Okay, so first up, Audrey, who is already sharing her slides. And Audrey, you can feel free to start whenever you'd like.
Well, the rules are settled, so I'm going to put my on. Thank you very much for. My name is Audrey Brouillet. I'm a postdoc at the French Institute of Research for Sustainable Development, and I'm a climate scientist. So if I have any questions about crop modeling, I hope I'll be able to answer this. So today I'm going to present you results about a project we are conducting under the AgMIP using AgMIP10. And I'll present you results about a paper we are going to submit very soon now about local increasing rainfall that is offsetting, according to climate simulation, the adverse historical global warming effect on lizards in sub-Saharan Africa, according to crop models. So by context to start, many studies, few studies have been showing that these years can be affected by increase in rainfall and possibly associated loss of nutrients, especially in sub-Saharan Africa. But relative contribution of combined warming and rainfall changes has not been that much explored yet in such low input systems. So in this context, we really wanted to continue this kind of studies and this kind of to answer deeper to answering these questions. And we have three major objectives for conducting this study. First, we wanted to compare multiple crop models' response to historical climate changes. Second, we really wanted to evaluate the specific contribution of rainfall levels of rainfall and temperature on years, again using crop models. And the third objective, main objective, was to investigate the attribution of such changes to global warming and possibly determine how this global warming affects yields in low-input systems. So we mostly focused on 5 sites in sub-Saharan Africa, so 3 sites in West Africa and 2 sites in East Africa here, so Mali, Benin, Ghana, and Ethiopia and Rwanda, was again varying climate conditions, varying soil types, texture, or soil management conditions. In terms of methods, we use and focus 4 climate datasets used as weather input for crop models, so weather station data and reanalysis datasets. I'm not going to talk about these 2 today, I don't really have the time. But mostly we perform crop simulation using factual climate simulations and counterfactual climate simulations. So for those who are not really used to this kind of simulations, factual simulations can be considered as an alternative historical climate simulations. Here we used from the MRI climate model from according and thanks to a colleague in Japan. And we compared these factual simulations to a similar set of simulations, similar counterfactual simulations. So we use the same climate model, but this time taking off not accounted for the human influence, the human activities forcing. We compared those. We compared in terms of climate, we used them as input for crop models, and we compared crop outputs, crop model outputs results. And if you have a difference between this kind of these 2 simulation sets, you are able to determine an attribution to determine the climate change effect. So the crop simulations were performed over the period, the historical period between 1918 to 2019 under present-day management, and we analyzed these simulations. We performed such crop simulations for each year, each growing season individually, and focusing on four crop simulation types. I'm going to present them along with the results I'm going to show you in a few slides. So here is a list of the 10 models and 10 model materials that agreed to get involved in this project. And today I'm going to present you a result based on 8 crop models under these 10 models, because we still have some output data issue, unfortunately, for 2 of these crop models. So first, the result in terms of climate simulation, so only based on the MRI climate model. On the left, what you can see is the climate change effect, so typically the difference between factual again and counterfactual simulations. The climate change effect on real temperature locally per sub-Saharan site, so Ethiopia, Ghana, Rwanda. When you have a value x-axis that is positive, it means that you have the climate change global warming effect that increases the given metric, so here temperature. If you have a negative values for the coming slides, it means that climate change decreases the variable. So what we were expecting, what you can see on this figure, is that global warming increases locally for all the sites, increases local temperature during the growing season for all sites, so around 1 to 1.2 degrees more during the historical period due to human activities, due to climate change, and around 1.5 to 1.7 degrees annually. In terms of rainfall this time, here is a corresponding graph, so some comparison. What we find is that climate change here results in more rainfall. So in Ethiopia, in Ghana, in Rwanda, and in Mali, there is less rainfall than here. Obviously, here we must be more cautious with the results. So because as you can see, there is more internal variability for the climate model, more uncertainty with the climate model here for the value, but the T1 media still shows this result, so more rainfall for all African sites, but in Mali. So in terms of impacts on maize yields, so this time based on a crop model simulation, here are the corresponding graphs, so the effect of climate change on potential maize yields for all the crop models that I've mentioned earlier, and the multi-crop model represented by black cross here. So potential yields typically allow us to account for possible result here in this case without water or nutrient stress and determined by a reduced number of variables. So what we can see here, this graph illustrates is that the warming effect, the local warming that I've just shown you, result in an adverse effect on maize yields in all sites in Ethiopia. On the graph, the black cross here, it's with negative values, negative difference between factual and counterfactual simulations. So the climate change historically reduce the potential yields according to crop models. So I don't have the time to show all the diagnostic here, but this potential yields figures mostly and results. From shortened growing duration for all sites. There was a decrease of the growing duration for all of the sub-Saharan sites. And in the case of Ethiopia, where the potential yields, it's a site where potential yields increased during the historical period, it's because the site is located at very high altitude, so the reduced core stress due to the warming offset the corresponding shortened cycle. When performing crop simulation with this time water related maize yield simulation, so this time accounting for the water stress, what the crop models, the 8 crop models have shown is that the increasing rainfall decrease the water stress, and the decreasing water stress due to climate change offset the adverse warming effect in 3 of the 5 sites in the region. So in Ethiopia, here on the top, in Ghana and in Rwanda, we have a total effect of climate change that increases water limited use during the historical period. And this is due to the increasing rainfall that offsets again the warming effects that we have seen on the potential years just before. However, in a site like Benin here, despite an increase in rainfall due to climate change, it's not enough to counteract the adverse effect of the local warming. And in Mali, there is, we've just seen that the rainfall was decreasing due to climate change. And this addition to the adverse warming effect, it is to with the climate change that reduce by up to 5% the simulated water limited maize yields. When accounting now for all stresses in crop simulation and in maize yields, so we simulated as well actual yields, this time accounting for temperature, rainfall, water, and nutrient stress, but without addition of fertilizer or nitrogen fertilizer. And what we found is that we find an increase of nitrogen stress for almost all sites but Rwanda. But this effect is increasing the nitrogen stress is relatively small compared to the decrease, this very strong decrease of the water stress resulting from the increase in rainfall. So what we found is that the change here in the actual yield simulated is very, very similar in terms of sign to the water yields changes that I've just shown you on the slide before. And what is not shown today on the slide is that calculated as well the nitrogen stress, the water stress, and the nitrogen stress is 2 to 4 times smaller than the effect of climate change on nitrogen stress is 2 to 4 times smaller than the effect on water stress. And something very odd and something that is both challenge, I think, and also limitation is that we were expecting to find evidence according to the crop models of very increasing nitrogen leaching due to the increasing rainfall that we have shown. But so far, we did not find such evidence. So this must be kept in mind for later discussions. So take-home messages, local warmings in sub-Saharan Africa due to climate change, local warmings result in an adverse effect on maize yields for all regions but Ethiopia. Something I didn't show is that this is amplified when we consider and when we activate heat stress input models. Second is that we find evidence of increasing rainfall during the historical period that offsets the adverse warming effect for 3 sites, Ethiopia, Rwanda, and Ghana, but it's not enough to counteract the adverse warming in Benin. And we find nitrogen stress that increases due to climate change, but only slightly compared to the huge increase in water stress for all regions. And our 8 model set does not show evidence of increasing the nitrogen leaching, although it was what we were expecting. So there are still things, next steps, next ideas we have to go deeper in this kind of studies, again, whether a challenge or a limitation. And one of them, the third dot here, is that we would like to investigate the responses per crop model. We would like to be able to say, okay, this crop model say this is the effect of climate change according to historical simulations in comparison to this crop model, to be able to address and to orientate how crop models can be used to address such analysis. Thank you very much.
Thank you, Audrey. And we have 2 minutes for questions. Yeah, please.
Hi, thanks for the presentation. I'm just wondering about the signal in the precipitation change in this region. So you said you use one climate model and you find that the increase in precipitation in this region, but I'm also thinking about like different climate models can also show different responses in regional precipitation change. So have you also considered using a multi-climate model approach to look at the precipitation trend in this region?
and it's something to keep in mind, of course. But yes, we actually as we completed this analysis over the historical period, it would have been a tremendous amount of work to include many climate models, many graphs per climate model. So what we did was to compare the corresponding rainfall trends and results to normalize this climate analysis. So on the all sites, over all Africa, all sites, and also compare this climate models results analyze this to also weather station in situ data to be able to say, okay, the model is out of the range, or if it's okay. Spoiler alert, it depends on the site.
So it seems like it was some kind of evaluation exercise. Is that right, Audrey? Right. Okay.
We did a very, we did not perform an evaluation itself. There is paper about, I can send you for the specific climate model, but we kept observation and analysis to be able to validate, maybe not, but evaluate, assess a little bit the climate model. Yeah.
Thank you. And just one quick question. Yeah.
We know that better farm practice also impacts the root development, and this gives more resilience to droughts. So you have considered that in the models, or the root distribution it's fixed between the two scenarios?
It's a very good one. Actually, I'm not sure. Each crop model has its own way. We have a detail of all processes that have been included in each crop models, but I'm not able to answer you right away, right now. But it was at last AgMIP 2 years ago that we discussed a lot during the side meeting about this kind of specific processes that must be taken into account. Yeah, but it's some crop models take into account, but not all of them, obviously. Yeah.
Thank you, Audrey, for that presentation. And you'll be able to hang out, I think, hopefully online for the session. Okay, great. Florian? Yeah. Thank you.
Do you have a...
Yes. And so let me take that. Let's give this a shot.
Okay, thank you.
Yeah.
So thanks a lot for having me in the session. I want to advertise my new model. It's a crop suitability model, just for letting you know what is a crop suitability model, because maybe some people are not aware of that. It's not a process-based model. It's also not a machine learning model. This is a fuzzy logic model, which I would classify into a category of empirical model. So which one? This one maybe? Okay, so as you all know, we already heard yesterday, land is a very limited resource, and land is also in the title of the session. That's why I'm here. That shows you, we already use most of the suitable land for agriculture. We focus, the best land is used for irrigated cropland. Then this is the cropland. You already also see that urban areas are mostly also located in areas that are more agriculturally suitable. And then you have the forests here and the grassland areas that are left, actually, but it's still growing and expanding. And we just published this paper. It just came out in February that I developed that together with a student that has been financed by CTIAR and CIAT and Benjamin Poschlot from the University of Hamburg. It's all open source, and and you can find the paper here with the link. Our focus in this crop suitability model was applicability. So it has a graphical user interface. This crop suitability model has several advantages, but also disadvantages in comparison to process-based model. The first is it's computationally very efficient, and it's very easy to parameterize. And that's why we can apply it at very high spatial resolution. globally, and for many crops we already have more than 60 crops parameterized. And this is like the graphical user interface. It's very, we try to focus on like easy to use applications, so that maybe also TOs, NGOs, or even farmers may apply this model at the regional or local scale. That's the crops. We have already run the model for Africa in the first application study. Yeah, it's a lot of different crops, and here we focus especially on crops that are important for Africa, for smallholders, like cassava and a lot of other crops that are often overseen in global studies. Also, we have cocoa, which is now a kind of a focus crop for me, since I'm situated in Switzerland now, and there is a huge cocoa, like chocolate industry there, and they have a high interest in cocoa also, and also coffee. So we have Robusta and Arabica also included in our study. In our graphical user interface, you can set the model domain just very easily with the mouse. And then you can, that's like the membership functions of the fuzzy logic approach. So you define different membership functions, and you can also graphically quite easily do that. And then you have also the opportunity to to set different other things that you need to set up, like all the input data and so on. And the model also includes an analysis tool, so that when you have your results simulated, you can visualize your results and compare it with different time periods and so on for different crops. So that's also included, and that's why we call it suite. So it's a complete suite of pre-processing the climate data, running the crop suitability, and then also analyzing the data. So the model requires different input data, climate, crop parameters, soil and terrain data. Then we have included a spatial downscaling for the climate data. So that allows us to really go to the very high spatial resolution. That's a statistical downscaling approach. For the climate data, there is some pre-processing required. Then we calculate climate variability also to consider that in specific. Then we get a climate suitability. For the soil data, we get a soil suitability. And then combining these two, we get a crop suitability. And then we have a lot of different outputs that are really interesting. From climate variability, we can calculate the recurrence rate of potential crop failure. We get the climate suitability. We get optimal sowing and harvest dates in the model. We can consider multiple cropping, and that's really interesting for integrating also different cropping systems, especially in Southeast Asia and other regions. We have the crop suitability. Also, we can look at the limiting factors. So is pH limiting, is precipitation limiting, or temperature? And we also output the soil suitability. That's how the membership function in general works. So you can define, like for temperature, for instance, you can define a belly curve and classify your membership, your fuzzy logic memberships. And that's kind of easy. Even like a farmer can actually do that maybe quite easily from his experience. So to say for values between 0 and 100, 100 means it's highly suitable and 0 means it's unsuitable. And in between, you can define different classes of suitability. And then we have a lot of different, mainly temperature, precipitation, and a lot of different soil and terrain input that we consider and have different membership function for each of these parameters. And then we apply the Liebig's law of the minimum for all of these different functions. One of the options that are most interesting in terms of also adaptation to climate change is the model simulates the optimal sowing date, and therefore we have a moving window over the year. So we simulate all possible sowing dates within a year, and then select the highest minimum value according to the law of the minimum, and then we get the optimal start of the growing period. And that takes into account like precipitation and also the seasonal course of precipitation and temperature, and that's really interesting also to combine that with multiple cropping then also. The model considers multiple harvesting, what I mentioned, but also you can consider irrigation. I cannot in detail explain all the different features in the model now, but like what you can consider also is germination requirements, different lethal temperature thresholds, different also photoperiodic sensitivities of the crops. And here you can also set vernalization requirements for winter crops. So that's but it's all not processes that are considered, it's all membership functions. For the climate variability, we have different thresholds, like for instance, the 95th percentile you can use, and we use that to then also define a membership function for the recurrence rate of potential crop failure, which means that, for instance, if you have a 20% recurrence rate, so you have a crop failure every 5 years, this membership function goes down to almost 0, and that again affects also the sowing date, the selection of the sowing date. Okay, so I already explained that, so I can go through that. So here's some examples of outputs that we already generated this model. That's the suitability of the most suitable crops of all the 50 crops that we considered here for Africa. And you can already see that the high spatial resolution, 1 kilometer spatial resolution, gives you very interesting patterns. And on the right, you see the most limiting factor for like, that's just an example for maize, but we have that for each of the different crops. And what is like really interesting is to see this area here of the yellow area, the orange area, climate variability. So here, the climate is so variable that you have a crop failure more frequently than 20%. And that actually, that's really interesting because there is still agriculture going on there, we found. And that's mainly the subsistence farmers that have to use this piece of land because they don't have any other opportunity. And in the inner tropics, pH is mainly limiting because soils are more acid. And yeah, and yeah, that's, I think, a very interesting output also because this output can only also, you can on the pixel base, but this is showing a transect at the 20° east line. But you can output all the different limiting factors also at each point. So you can see, for instance, if you're here, if you are able to eliminate this factor also with your management, for instance, then what is the next limiting factor and so on. So this is maybe helpful really for the farmer on the field, or can give actually some consultative information that may be helpful really at the local scale also. This shows you also, again, the impact of the climate variability, what I also highlighted before with the orange area. So that are the regions where we see a loss or a penalty on the crop suitability because of the climate variability. So these are, like, maybe not surprising, the regions where climate is really variable, and also precipitation is variable, and that impacts directly on the agroclimatic risk that the farmers really experience there. Yeah, we did a study here for United Nations South Sudan mission, and that focuses on South Sudan and North Sudan also, because here is like a very farmers are very vulnerable to these to also this variability. And the second region that is very vulnerable to this variability is also Mozambique and the southeast of Africa. That's the possible number of harvests, like a potential for multiple cropping. I think that's over all crops. So how much is the potential? So here you can see 1 harvest, 2 harvests, and 3 harvests. But you can have this information specifically also for each crop. And this shows you how many crops are suitable, actually, of like the ones that we considered at each location. And there's also a huge range of different, of like regions that can have more opportunities for growing different crops, and those other regions that are kind of limited. That was the past. Also here you have, as an example, the optimal sowing date for maize under the current climate. And here I show you the change of the optimal sowing date under SSP 585 for the 2040 to 2060 period. And that's also, just an example for maize. And if you have the raw data, you can really zoom in a very high detail, in a very high spatial resolution, so it can give you really very precise information. And the shift of sowing dates is also quite large. That also questions if labor is available, etc., etc. So that's the study that we did for United Nations South Sudan mission South Sudan, and there we identified that's the suitability under future conditions, just for the combining rainfed and irrigated areas, and that's the historical period. And as you can see, there are some winners, so we can call them opportunity crops, but there are also losers like sesame, which is unfortunately one of the most important cash crops in South Sudan. But there are other crops like maize that are where the suitability increases. But still, for the losers, we found that there is kind of potential for shifting the areas into other regions. So needs also to be can also be seen in the results and needs to be considered. As I mentioned, in Switzerland, we have focus. Yes, we focus also on cocoa. So that's just very preliminary results. We are now also doing global simulations at 1 square kilometer. And because cocoa is one of the most sensitive crops to climate change that I've ever seen in one of my simulation results, you can see that there is really high impact, especially like in Western Africa, that produce, like Ivory Coast and Ghana, produce 60% of the cocoa, of the global cocoa production. And there's a huge damage in the suitability of cocoa. And there are regions that are not at all growing cocoa, and also having different climates that are becoming suitable. But that asks a lot of questions of, like, for instance, pollinators are available there in the future, and so on and so on. So that's just very preliminary results that we have already produced, and also are in contact with the Swiss chocolate industry to bring this to the stakeholders. So what are current activities? How can we use this model? We still are writing a paper on climate change impacts for Africa, also in cooperation with CTIR. And then we want to also look, because of the high resolution, we want to look into the urban catchment areas because of the high urbanization processes going on in Africa, and specifically concentrate on these, how the suitability changes in these urban catchment areas. Then, of course, we want to identify sowing date and also different opportunities for different crops. So you can call that land use adaptation or whatever. Then we aim at expanding our simulations, not only for Africa, but also to make it global. Therefore, we want to use the 5 AgMIP, CMIP6 climate models for like the almost 60 crops, or even more than 60 crops we have now already parameterized. The integration of extreme events is a big topic, because that approach is so like a simple approach where you can use like also meteorological indicators to consider extreme events, and that's like frost and other events that we specifically want to integrate in our approach, also together with the University of Hamburg. And then there's that's the extreme events, frost, cold waves, heat waves, and drought is a focus. But also we want to include biotic stresses. I think it's not on the slide. Here, pollinators, pests, and diseases. That's something that we can integrate also with a membership function, because that fuzzy logic approach allows that also to do that, not in a process-based way, but in a more like a risk analysis way. And that's, I already mentioned, excessive precipitation. We discussed already in other sessions, it limits field work, and that's a huge issue. If you look into participatory studies, that in many regions in Brazil and also in Asia, heavy precipitation events during the harvest or also during the sowing is a huge limitation, and that also we want to consider in the future work. So thanks a lot for your attention. The code is written in Python. There's the code is on GitHub and also on Zenodo, and all the data for Africa on 1 kilometer, like all sowing dates, etc., are also on Zenodo available.
Thank you. We can take one very quick question while I switch slides. Oh man, whose hand did I see? I think I saw you. So go for it.
I have a quick question. How do you define suitability?
How do you
define suitability?
Define? That's a good question. I tried to briefly did that in the beginning. Crop suitability is not clearly defined. It's a kind of potential for land use. So what crops can you grow there at all? Is a crop suitable or not? And also it gives you a kind of a classification. Is it good, suitable or not? You could also apply crop models. That's another way of and simulate yields, and then also say, like, if the yield is high, you have a high suitability, and if the yield is low or zero, you have a low or no unsuitability. So that's also something that suitability can also be done with process-based models. So, but we use a simple approach that has some advantages that I highlighted here, but yeah. The definition is like not, maybe there's not like a clear global definition of what is suitability.
Let's have a follow-up discussion.
Yeah. Lots of questions.
I guess we all have questions.
All right. Thank you very much. Okay, Thomas, next. Great, and you can use this, and I will let you know in 15 minutes. Is the big button to advance? Okay, great.
Thank you.
No worries.
Okay, hi, I'm Thomas Oberleitner from the International Institute of Applied Systems Analysis. I usually work on data science problems in my group. And I want to introduce you to our research regarding identifying the drivers of yield anomalies in global gridded crop models. So apologies to all the GGCMI folks that already heard pretty much the exact same thing. But I tried to remove the more confusing slides, so this is a bit of an improvement.
It's a little delayed.
Okay. So we're looking into the GGCMI phase 3A crop model ensemble, which is a state-of-the-art crop model ensemble. Yeah, and they share like a simulation protocol and create simulations based on this simulation protocol that they're defining beforehand. But because of the different backgrounds and different implementations, there are a lot of differences between the models. For example, the photosynthesis type, the response to stresses, or which stresses are at all available for different crop models, the response to CO2, they're calibrated on different data, and so on. So there's a lot of variability in how they work. And this is also reflected in how they create projections and simulations, especially for the future. So here you see this huge divergence between the predicted, here the productivity change, the predictions of the crop model. So we see that GGCMs produce different outputs, which is kind of similar to saying they're sensitive in a different way to inputs. And this is why we are using a classic sensitivity analysis, in the sense of we're analyzing a system with a meta model that we're evaluating instead of the real thing. And our research questions are: what are the drivers of yield anomalies? How do different GGCMs differ in the sensitivities? And what is the impact of input interactions, which is something that is often neglected. Okay, so this is our study design. We're using a bunch of climate data, also used for the simulations themselves. Those are daily data. We then create some derived entities from those daily data, like the heat unit index, leaf area index, PET, and then we aggregate them into like a growing season quantity. For the yield, so this is also for rain-fed maize. We are looking at the time series from 1970 to 2015, and this is the range that we're using for normalization or trending of the yields. So it just works basically by just fitting a regression line through the time series, and the relative yield is then defined as the distance of those points to the regression line and normalized into a fraction. And what we identify as its yields is everything that is below minus 50% of the expected value. So we have our climate feature aggregates, we have our yields. We also include the Köppen-Geiger regions because we fit models on Köppen-Geiger main classes. And we also include the harvested area span. So we only get the data where it makes sense, where the crop is actually grown. And also soil and fertilizer input data. And this is then what we use all merged together to train our gradient boosting models. So this is not a regression model, this is a classification model that only is concerned with is this observation a yield anomaly, or is it not, towards probability? Based on those meta models, we create Shapley values to identify how important input is, and also how important interactions are. So this is the occurrence of yield anomalies in the data at all. So overall, we see there is a strong variability. It goes from 3% to 50% across all the climates. But there's also within the climate a lot of variability between the models. So Simplace shows the highest median rate across all regions, and AgMIP10 the lowest in this case. But this is also something that needs to be considered when fitting a meta model, right? You need to weight the class probabilities to reflect how they occur in the data.
Speak a bit louder, please.
Oh yeah, sorry, sorry. Microphone. So the features we're actually investigating are, first of all, climate features, as said in the pipeline. Those growing season aggregates. Those are the wet number of wet days, heating degree days, killing degree days, frost days, ice, number of rain days, consecutive wet days, and dry days. So we have all those hot, dry, hot, cold, wet impacts. They're all considered. And we also have as measurements the fertilizer input and a set of soil features. So sand, silt, available water content, and organic carbon. But this is all the result of a long process of identifying features from a much bigger set of features. Some of them, for example, the average temperature or the growing season. So yeah, but these are the ones that we're looking at. So just a couple of words regarding Shapley values, which is what we're using to identify how important a feature is to the output. So they're a local estimate of importance as opposed to a global one, where you get one value for one input. For example, the number of rain days is 10% in importance. But this is not what the Shapley values are. They are, you sample, for example, 1,000 of them, and you arrange them across the whole domain of inputs, for example, the net rain days. And for each of these sample points, you get a value of how important it is. And this is what you see with those beeswax plots, where you can see the effect of the number of rain days onto the probability of a yield anomaly occurring. And the nice thing with Shapley values is you get this distribution, so you get much more information. And you see that high values of rainy days have a much lower, actually reduce the probability of a yield anomaly occurring, and a low value in blue increases the probability. And because we can't really produce those plots or show those plots for each GGCM and each climate that we're using, we want to aggregate all the GGCMs per climate. And so we collect only the most meaningful Shapley values, the most extreme ones, the top 5%, and average those. And this gives us one single box per crop model that we can then put on this x-axis. And yeah, you see this comparison of all the models per feature. And also a small detail, like the position in this y-axis is how clean this bee swarm is. So in the middle, you have the noisy ones. On top, you have positive correlation going from small to high, and high to low at the bottom. Okay. Into the results. So we do this for every climate region, so A to E. But this is just an example for, and the results look similar across regions pretty much. But this is the example for Köppen-Geiger region A. Here we have the order of the most important features that we investigated. So precipitation comes out on top usually. It is as the main contributor to yield anomalies. It shows the strongest impact in Simplace, the weakest in Kroger. So here we have Simplace, on the other end, the 2 is Kroger. 14 is actually the Izumi dataset with real observations. And we also see that all those boxes are blue, which means that mainly low feature values are associated with yield anomalies, which in this case with rain means drought. There is this one outlier, which is sigma, where the opposite is actually true. It also contributes strongly the yield anomalies, but in this case, with high feature values of rain. So this is an indicator that excess water contributes more to yield anomalies. And on second place, we usually have temperature-related features. Yeah, but overall, there's a large spread in those results. And what we see here, just when investigating anomalies specifically, we see that soil properties don't contribute that much. We also had a look at the interactions. So this is a big data set. It was even bigger than the Shapley value data set to actually explain and meaningfully show. This is why we only show here the number, the frequency of interactions between inputs that contribute to more than 5% to the yield anomaly. And we see roughly that in 20% of the sampled cases, interactions between the feature values, and those are independent of the actual features, of the actual importance of features. Only their interactions are contributing 20% of the cases to the yield anomaly strongly. And this also reflects the complexity of those models, because we have features that are interact very strongly and autocorrelate. And yeah, they're very complex models. Just as an excerpt, this is another crazy plot. But basically the message is it connects features that are very strongly interacting. The main message is that precipitation and soil texture features are the strongest interactions that we found here. So, for example, we see here a lot of arrows or a lot of lines going from the rain days to sand or to silt. And then we have what we also found is a lot of interaction between temperature-related features and fertilizer. But yeah, again, those are very varied results. Okay, so in conclusion, we found precipitation, specifically drought, is the dominating contributor to yield anomalies, followed by temperature features. We have this outlier with sigma that shows us another sign of the feature value that is more excess water sensitive. We also saw the importance of interactions in our analysis, and yeah, we think this would be a kind of generic framework to investigate the effects of any set of crop models into any set of data, because very flexible in that way. And the outlook is basically all of them are related to avoiding correlations in the data, which for these kinds of analysis is often can produce very conflicting and nonsensical results if you have correlated input data. So maybe the creation of a really uncorrelated or nearly uncorrelated data set would be worth investigating. And then there is some technical advancements in the, for example, Shapley library, because now we use a method that is kind of susceptible to correlations. You can have better sampling or better meta models that are more aligned or more structured, like the real thing. For example, they could work on a daily time step, and then you get a more clear signal about the input sensitivity. Okay.
Thank you. We have a couple minutes for, go ahead, Drew. Yes.
Just real quick, we already talked,
Yeah.
and we will talk. Fantastic, happy to see this, really excited for the work. Technical note, you were qualifying an anomaly by 15% from the mean. I wonder if your feature selection changes with that threshold. Maybe more extreme anomalies have different drivers. So that will be interesting. I don't know if you looked into that.
Yeah.
And the second point is real quick, the solid properties. I don't think that would have a big influence because they're static over time. So they don't contribute to anomalies. And then the third point is, and we had more yesterday, so the residuals is the big one. But are you then trying to use this to look forward? Are you creating a future looking model?
Yeah, I think that's on the to-do list. Yeah. I mean, it really independent of the data set. So I think we had that was the plan at some point. Yeah. But yeah, I don't know really. There are no concrete plans, I guess, no. Sorry, what was the first one?
Anomaly threshold. If you take a higher anomaly,
so we actually, we started with a couple of different ones. and the results change slightly, but but not in a major way, really. Precipitation still comes out on top. But yeah, we just used the 50% bit because it's also used in other literature, like for example, the Ben Ari paper that looks at the anomalies in the French breadbasket. But yeah.
I think I saw this, yeah, and then we'll continue.
Yeah.
Lisa, I think it's a brilliant presentation. It seems you've been able to unravel how different, climate drivers and the behavior of different models. Is there any plan to understand which model is right and which one is wrong?
I think there are other experts here that can answer this in a better, yeah. I mean, this could be a tool to maybe help. I don't know. What do you think?
Well, to add, we discussed, you can look you can take the tool to understand drivers of the anomalies, but you can also look at the residuals between observations and the model simulations and use the tool on the residuals to understand what's missing. And I think that would be very informative to select models that can address certain questions.
I think those are the residuals. So the difference between the simulated value and the actual observed value, right? These kinds of residuals. And so you get like a sensitivity of how far are you away from the real thing and what are the drivers for that. I'm very interested in that.
So thank you very much, Florian, for this. And I think we'll have hopefully maybe a few minutes at the end, but I think Heidi, I know you had a question, it's burning. So if you want to ask it while I bring up your slides, then
okay. Yeah, it was, you use a half-degree data, half-degree simulations.
Yes.
I wonder, because then there's a lot of spatial averaging, and especially like for this wet signals, you probably lose them, I guess, by the time you're at a half degree, whereas drought signals are usually more systematic. So I wonder, it would be interesting if you like just in a case study looked at really fine level data and compared the signals, or if it, because there's probably very little like physiological response anymore at that aggregate level.
More really high resolution data sets. Yeah. Thank you.
Do you want me to give you a warning, like a 2-minute warning?
Yes, I think I'll be quick.
Okay, I'll give you a 2-minute.
Okay, thanks. Okay, it's great to be here, but I definitely feel I was put in the wrong session. This is really a crop model improvement study, and I guess because it deals with how our crop models are simulating daily evapotranspiration that we landed here, or they were short on a presentation.
I think that's fine. I didn't choose these.
Yeah, so don't be disappointed. Maybe this is just as a warning.
We're looking forward to it.
Yeah. And it's part of the AgMIP weight team. Oh, sorry. Part of the AgMIP weight team. And I put this up because as a bit of also to make sense of why we're here. We've been working a lot on basically temperature drivers, crop growth, and I'm especially interested in temperature drivers of phenology as it affects timing and exposure to extremes. And so crop temperature is commonly used by breeders, and we really interacted a lot with the people here at CIMMYT on this as a really great, cheap, easy field phenotyping method to pick up drought and heat tolerant lines. And this, I think, is a really nice picture showing this is irrigated and rain-fed turf grass somewhere in the US. And you can see here in this thermal image, temperatures ranging from the low 30s up already to probably close to 50 degrees. So same air temperature, and I'll pretend that's there's a temperature sensor in the back building there, but you really see this huge variation. And the main source of variation is, of course, if it's irrigated or rain-fed. And then you see a lot of within field variation, if probably with this combination of local soil conditions affecting plant growth, and then as those have changed water availability. And normally in our crop models, we are just using air temperature, so you don't get this temperature effect due to different water availability. So we did two really nice studies in AgMIP wheat looking at simulating canopy temperatures. And long story short, our models were generally very, very poor. We could explain with the best models in some environments, maybe 50%, and that other models were explaining maybe 5–10% of variation in field observations. So our question was why? And looking at this picture, we see, hey, if we know there's obviously the main driver is water availability and then evaporative demand. So canopy temperature is really related to our simulations of drought or water use. So we thought before wasting more time on canopy temperature studies, let's check and see how well the models are doing with simulating water use. So just as a background of what we're doing, and then to fit in this session, I put in a map and just said we initiated a study where we wanted to assess, first of all, benchmark how well our models could do in simulating evapotranspiration. And then we wanted to kind of assess what are the conditions, environments that explain model skill, and are there particular processes that are really driving this error or uncertainty in our simulations. And we had data from 2 sites, one in Bushland, Texas, which is a semi-arid site, and then in Avignon, France, which is Mediterranean. I just put this map here to show those. Just take it in. And really nice quality data. One is lysimeter data with over 3 years with a full irrigation and a deficit irrigation. And this one has like daily evapotranspiration. And the data set in Avignon, France is a rain-fed site. And we just picked out the 4 years with wheat that were with no kind of frost damage or something else that affected yields. So here is just a first plot of the results. The gray points are the individual models, and we had 17 models, and the blue is the model median. And these are daily observations on the y-axis and the simulations on the x, and ordered roughly from the most water limited environment to the, the full irrigation where we think there is no water stress. And what we see across almost all of these environments is that our models are consistently underestimating evapotranspiration. And that was consistent, across the environments. And we also, you may say like, well, some of your models are definitely capturing that. But when we dig in a little bit more to this, often these models just have very little correlation with the data, and it's kind of a random. We do have one model that had a slope of close to 1. So we do have one model at this point that performed well. And what I'd like to show here, we tried to start to dig into where is this error coming from. So we separated our observations now across all of those 10 environments, and we show them basically in terms of what is the evaporative demand. So what was we just used the observed ET buckets. And in early vegetative, when you expect a soil water evaporation to dominate, full cover, the plants are green, and there's probably very little soil water evaporation. And this is a more complex stage because you may have full cover, but the plants are not transpiring. And you basically see that the errors, this is an absolute error. Maybe I'll summarize. The relative error is more or less the same everywhere, but it blows up at this 0 level. So we show this. So you could say the models are making the same relative error, more or less independent of the evaporative demand. However, we think that this very large errors that we see at high levels of evaporative demand are really then propagating into our simulations as large errors in the water balance. So if you're consistently over many days underestimating water use in your model, you will have more water than in reality. So you will kind of be acting to avoid drought stress to a certain point. And some of my co-authors don't like it when I say this because we didn't test this, but we think an implication of this is likely that we're underestimating drought stress in climate change studies. And one thing we checked, this red versus white, is if the models had correctly simulated these, what I'll call like growth stages, because maybe they just were off on their phenology. So you see that there's not really a clear pattern of that. But there's a little bit of a tendency, and depending also on how we define these stages, that the bad phenology simulations lead to bad LAI simulations, which also then can get your water balance out of whack, but we don't see any real evidence there. Sorry. Okay, so what is behind this error to help us in model improvement? We did a sensitivity analysis where we didn't look at parameters, but we kind of tried to consider model structure. And this is a subset of the models that used a reference crop evapotranspiration method, which is basically independent of the crop. It's just probably, as you know, an environmental signal.
Yeah, it's
Can I just touch anything?
No, I think,
You have to touch again.
touch it again, just to let's get it
Double,
one more time.
double click. Double click.
Do I need to
Double click on the screen.
again?
It's okay.
Very, yeah, we can follow it still.
Oh, sorry.
I'm not seeing on.
Very strange.
Very
Okay,
good.
so what we did is we wanted to vary, basically, you could say what we really wanted to do was vary how the models simulated reference crop evapotranspiration, potential soil water evaporation. This is the daily increment in root growth, so how fast the roots were growing into potentially wetter soil. And this is like the maximum depth the roots would grow to. But rather than insisting the models all make a model improvement at this stage, we just had people go into their source code, and at basically the last line of where they were calculating each of these processes, we just applied a correction factor. So plus 10%, plus 20, minus. So we tried to, and models had to verify that didn't introduce error to their models. But what we see then with this variation is that when we look at the output variable soil water evaporation, yeah, it matters how you model soil water evaporation. Not so surprising, but close to 50% of the variation across environments is still related to these two demand terms. Sorry. And then if you just look at, the sum, the evapotranspiration, this, except in the driest environment, so it's dry to wet here, there it does matter what you're doing with soil water evaporation because you have a smaller amount of water. So if you're overestimating that was introducing variation. But for the most part, we really see these demand terms are describing most variation in the models. And we saw a similar pattern for models that directly use something like a Priestley-Taylor approach, a potential evapotranspiration. That's what I said. So then the next thing we thought, aha, though, are we doing better with the models with reference crop or potential evapotranspiration approach? And this is a really interesting one, and it's a bit complex, but you could just imagine like blue is a model that is performing very well in a certain environment. So again, these are the dry environments to wet, and dark blue are the top ranked models in that environment. And it doesn't matter if we use RMSE or a correlation. And so the couple of interesting things here, good models tend to be good in all environments. We often say in crop modeling, oh, this model is good for this environment. But in this case, we didn't really see much of that, but mind you, there are two specific environments. And the other super interesting thing is that we had 4 DSAT family members in this, and they're not identical, but basically the DSAT models that were performing the best didn't matter what ET method they were using. So here's this, I won't identify it, but DSAT model number 1, it was ranked in second place with an ET0 approach, and in third place when it used the Priestley-Taylor. And then if we look at this end, there was another DSAT model that didn't, it's actually quite different, but it was one of the least performing models, irrespective of what it used to model potential evapotranspiration. So at this point, we said, oh, why didn't we ask Daniel Wallach at the beginning? Because there's a big artifact of calibration and modeler here. Yeah. Which it scares us a little bit. Yes. Yeah. So yeah, the modeler effects dominate. I won't go into this, just simply to say we don't see super strong relationships with either LAI or the available soil water. And we have really not dug in enough to this information on the water balance yet, but we think with this importance of the demand terms that, yeah, we're not so surprised by this at this point. I think I'm at the end. Our median underestimating ET across environments. And here I have to give a caveat. I just saw the soy team, they did a study in a humid site in Canada, and they found the opposite effect. So I think we really need to start to talk across the teams and ideally, have to really learn what are they seeing. So to take this with a grain of salt. On other environments, the soy models are really overestimating water. We think, though, for this case and in these environments, it means our wheat models have been underestimating drought impacts. And some of our next steps would be to use a machine learning approach, Trent is not here anymore, to really look at what are the real drivers on those demand terms. Go back, some of the models did not directly report their ET0. So we want to actually, are people just calculating that incorrectly? Maybe we do a little bit of an application, somehow scaling the results to semi-arid regions. Yeah. And yeah, we definitely want to talk with these other teams. The maize team confirms these results for their studies, but the soybean team, very different. I think it's probably worth looking into a bit more. And that's it.
Thank you. I'm curious with the drought impacts and likely underestimating. Have you done experiments where you've just hit the model with historical drought conditions and like how does the model like? I mean, you're saying likely underestimating, but are you actually seeing evidence? It seems like it would, but
I mean, no, we haven't. The closest thing that I have in my mind now that we've done is when we did European level studies. So again, with very aggregate level data, there we could see that the models for maize really pick up drought signals. Yeah. And whereas our wheat models just have often a negative correlation with precipitation signals because they were not sensitive enough. This is a study 5 years ago to the waterlogging effects. So now we've invested a lot in that. And so for really strong droughts, we do pick up those signals. And but it's a good idea to, but our wheat crop models, we've seen this before, at least in Europe, in England, Denmark, Germany, a negative correlation with precipitation.
So as you get into the more humid mid latitudes down.
And in these environments, though, where I mean, you could also argue at least our model is developed in the Netherlands, and then to apply it in such environments is,
Thank you. Go ahead. While I'm changing up the slides. Please.
Okay.
Yeah, go ahead.
Yes. I was wondering, because like most of the crop models I know, they do not consider canopy or leaf temperature. They use maybe the air temperature, but for calculating the growing degree dyes, the photorespiration and carboxylation and so on.
Yeah.
So is that, I mean, there are some models like the Promit model that I tried also using a leaf temperature instead of air temperature, but then it was not conform with the protocol in GTCMI, and then we switch back again to air temperature and so on.
So right now, I think like I said, our canopy temperature simulations in general are not very good, and we think they're.
Are they also feedback?
But I can also say the way with most of the models, I think all of them are using except the new DSAT energy balance they implemented, they use a single source energy balance, which basically assumes all energy and fluxes are from one surface that's dominated by a crop surface. So we're now developing with the colleagues in Montpellier two source energy balance model that separately does an energy balance for the soil and the plant, and that way we could generate like a plant temperature that we think is important.
Yeah, and also like which like from my experience, you should maybe also think about differentiating sun.
This Montpellier model does that. They do it, and we're trying to so they have a 3-source, like the shaded sunlight, and we want to try and go with 2-source to also reduce the complexity, but that will be an interesting comparison.
Sonali, this is Alex online. Can I squeeze something in?
I was just about to call on you. Go ahead, Alex, real quick.
Yeah. I don't want to disrupt too much, so I'm holding, but I just want to say I've really enjoyed all the talks in this session and have already composed some emails to people to follow up. Heidi, just very quickly, you mentioned LAI as another thing you could check and your phenology, but I wonder if you're looking at just overall biomass. You could have kind of LAI right and your biomass wrong, and that's gonna have a big effect on this. What we're finding is, when we evaluate some places, the LAI sequencing with phenology is pretty good, but year-to-year variation in that, and in some cases, the overall like peak greenness is really wrong. Thanks.
Yeah, you make a good, I didn't show it, but the model's got biomass, huh? Because we're so trained to calibrate. I show here the calibrated results. But I think there's more interesting results when we look model by model, which I didn't show here. But that's a good point. Yeah.
All right, thank you, Heidi. And I'm to.
So we change the mode, right?
Yeah, let me just. For a second. Okay. There's two zooms, one over there and one over here.
Oh.
So this should. Okay, let's try it. Sorry, on the schedule changed. So, okay, so I can't actually access it.
So you see the second slide already. That's cool.
Okay.
Spoilers.
See, it's actually coming up. Ah, here we go. It's just delayed. Okay, that's advancing. So hopefully that should work now. Just don't touch anything.
Back?
No, yeah, so that should be
backwards.
that good. Yeah,
Cool.
there we go.
Yeah, thanks very much. This paper is about actually connecting to some extent land, water, and climate modeling. So that fits to the session. This is a paper, a very complex paper actually, by Edna Molina, one of the PhD students in the MAGPIE group at PIC, my group. And I will focus a lot on the methods because we only have basically 10 minutes. But this is connecting AgMIP with AgMIP, the Intersectoral Impact Model Intercomparison Project at PIC. And well, the issue is, of course, land use change and socioeconomic drivers affect, or including agricultural demand, in fact, land use transitions, and that has a lot of effects on hydrology, on biodiversity, and things like that. So in the AgMIP, it's a long list of sectors, as they call it, different domains where people model climate impacts on hydrology, on biodiversity, on crops, of course, but the AgMIP GGCMI team is the agricultural part in AgMIP. And so the request to, and the several global land use models are, of course, part of the global econ team in AgMIP. So there has been quite a bit of interaction. And the issue is that these biophysical modeling teams, like the hydrologists, to take that example, to be more realistic, need land use patterns as inputs, right? And these land use patterns also change in the future. So how do we generate future land use patterns, which can then be used as an input to the other modeling sectors? So that was the task. And we had a first round where we only provided land use patterns from one model, from the MAGPIE model at PIC to all the AgMIP sectors. And then the next step, we said, but we also need to do multi-sector in that element because there are lots of uncertainties. So we started out with 3 global land use models: the MAGPIE model, the image model from PBL, and the GloBiome model from YASA, which are all able to provide gridded outputs at the global level. For various reasons, the GloBiome team in the end couldn't deliver, but Edna put together this paper where we were asked to provide to the AgMIP sectors land use projections, bioenergy crop demand, irrigated crop area, fertilizer use. You can imagine these are inputs useful for these other models. And then the protocol is like we took the 5 AgMIP climate model inputs, 3 different scenario SSP RCP combinations, and then these 2 model combinations. We only used 1 crop model here, so it's still limited, right? But we go step by step. 1 crop model, taking 5 climate model outputs, feeding them into 2 different land energy modeling systems, and then see what comes out to explore the variation, at least a bit more than we did in the past. And so yeah, the novelty of the paper. The paper, by the way, is almost, it's almost finished. The preprint is already available and will be online soon. I mean, preprint is online, but the final paper in Earth System Dynamics. So it's the latest CMIP climate data using CO2 fertilization effects. This is all harmonized with this LUH procedure, which is used in the IAM context. Yeah, and recent updates on the land use models. And just to show you really a extremely complex thing, what Edna did. So we, of course, had the scenario setting using outputs from the climate models, feeding that into the crop models, and basically then taking outputs on crop yields, on water availability, and soil organic carbon, and that feeding that into those global land use models. So first setting up the chain and collecting all this information, and then looking at the results, land use patterns, management levels in the land use models, testing these for bugs and everything, and then harmonizing with LUH, that's the group by George Hurd, which provide harmonized data for the integrated assessment models, also generating a consistent and coherent pathway from the past observations on land use to the future projections. And then finally, this is all a bit slow, doing this harmonization and then provide the inputs to the AgMIP core team, so that can be used by all the AgMIP modelers as they like. I mean, some AgMIP modelers, like some sectors don't need any land use information or socioeconomic information, but others do. And in AgMIP, they are trying to provide the option to look at climate impacts only, socioeconomic changes only, and then the combined effect. Again, if you think about hydrology, both things matter, and it's nice if you then can single out both dimensions. And very few results, only what you get for the different land use types. You get the results over time. This is areas, and you see then the difference, green for Magpie, blue for image. And you see for some of the scenarios, the two land use models are pretty close. But for example, for grassland, there's a huge variation. And also, I think for bioenergy crops, we see that later. And also, this can be looked at regional aggregation. These are these 5 IEM large regions, and in some regions there are larger differences, in others they are smaller, and it's also different across the climate and socioeconomic forcing. So you can already see lots of results, which I will not go into detail, but just illustrate here. We can also look at the maps and see where the coefficient of variation is large. To see this example from parts of Latin America, and this is about, okay, where is there already a lot of concentration on land use or management intensity, and if this differs across the scenarios, where's the coefficient of variation larger? So one output was that where there is already a lot of land use or concentration, this is forest now, concentration of forest going on, there is a relatively low coefficient of variation, and in other areas where there are bigger changes, it's higher. And one other nice thing which Edna also did is this decomposition on what contributes to the variance. Is it the global climate model input? Is it the land use model which is used, or is it the scenario setting or some interaction effects? And of course, you want to have this singled out by the scenario setting, because that's the main difference in drivers. But you see for different indicators, for cropland, for example, the main part from the variance comes through the scenario setting, but especially for grassland and bioenergy crops, a lot more variation is contributed by the land use models due to various settings. So the GCM influence on the variance is very small. Scenarios assumptions kick in after 2030, and the land use model selection, 2 examples, has an impact on the second generation bioenergy crop area, and also with respect to grassland. And then you can look at this across resolutions, and so on. So this is very fast. Lots of more results there, and then we also have to see what's the impact on the biophysical models, but that's then in the next phase. So some takeaway messages here. The global trends are similar across models, but of course we need to look at different regions, which we can. especially for the high emission scenarios, there are larger disagreements on grassland, forest, and other natural vegetation. Okay, bioenergy I didn't cover here, I dropped that. Yeah, as I said, higher uncertainty arises when land use area or management changes or decreases in different scenarios. I talked about the scenario assumptions. And again, second generation bioenergy crop, that's also covered quite differently in the land use models, but that's important for some of the biophysical modeling teams. So then the differences can be explored. And yeah, there are some differences with this LUH team. Historical data is also quite a complex process, but we're trying to find out where they exactly are. And that's about it. And you can see the preprint here. And soon this will be fully out. And then we'll see what the AgMIP modelers say and try to improve that in the future. Thank you very much.
All right, thanks. All right, time for questions.
Is it correct to assume that you just use the GCM data as inputs and the land use change don't feed back into the climate models?
Yeah, exactly. I mean, as you can see with this setup, somewhere you have to cut it off, and then
Sure.
feedbacks are there to a limited extent. But yeah, you have to start somewhere. And also, I mean, if you think about it, I'm not quite sure how but because LPJ also features the water balance quite well, so the results from LPJ on the climate impacts on water availability are already covered in this iteration. But you can imagine more feedbacks, of course. Yeah.
Do you want to talk more to the climate scientists to get their or your land use projections into the climate models, and then
this is currently happening for CMIP7. Actually, that's a new exercise that the land use modules of the integrated assessment models will provide their outputs for the climate models. This wasn't the case before. Until now, there was always this cutoff, and then you can argue it's somehow inconsistent. So now for this round, it's part of Scenario MIP, it's called. Scenario MIP is one exercise within CMIP. And we are right now busy, or not me, but all my colleagues busy generating those land use patterns, which then will be fed back into the climate models.
Cool.
So at least, step by step, we are getting to a more consistent picture. Hopefully. Cool question.
Just following up on that really quick before we move to the last talk. Does this change at all? I know there's been discussion, I don't know where it's landing, Alex, you might know, with emissions-driven simulations for CMIP7. And I am wondering to what extent that may or may not matter for the land use models and the projections for future land use change whatsoever. Is it just assumed that if you have, right, because you've got changes in land use that will impact emissions.
Yeah, and then you would have another round.
And then you might, and that might influence something else even
Yeah.
within the scenario narrative. And so I guess I'm just wondering, like, how, or is that just not being dealt with at the moment, and we're just kind of forging ahead with?
As I said, that would, I guess, be the next iteration, and ideally you would do like a multiple iteration until it converges or so.
Yeah.
But
Haven't done.
at the moment, I think that's too ambitious because you need a certain time to run
Yeah.
the IAMs on it, also to be harmonized, feed it into the climate models. I don't know how long it takes to run those. So you have always to be clear where are the limitations in terms of feedbacks and where you have to cut. Yeah. So, but it's step by step, and the nice thing is also with AgMIP, with this structured approach, you can connect more and more elements because there's a like a agreed upon protocol behind it. At least the same GCMs are used. Okay, you have to select, but the standardization of protocols across AgMIP, AgMIP, and so on, and the IAMs helps to at least facilitate the process.
Sonali,
Alex, yes.
Yeah, we've got
Yes,
Alex
hi.
real quick, and then we'll move on. Yeah.
Yeah, so I'm involved in the scenario MIP process that's developing these new scenarios. So I actually debated them pretty heavily on this point, and where we came to was that there really wasn't enough time for us to run the IAMs, run the climate models, then run the land use impacts, then feed it back into kind of an iterative cycle. So there's now language in that paper that talks about explicitly the simulations do not include like the societal responses, whether they're adaptation, mitigation, or just other shifts like this. Now, that's not to be said that they're not important. The paper also notes that an actual projection of the future has to include those things. So there's definitely room for AgMIP or EasyMIP or some combination of all of us to come together and say, let's take it to that level. It might be a year or two after the original scenarios come out, but we could be intentionally developing those scenarios, and that would be incredibly powerful. Thank you.
Yeah, thanks, Alex. I mean, that's one point, but as you saw in the slides already at this stage, you know, for example, this variation in grassland, right? I mean, that's something to be explored. Because of the livestock sector and how things are covered in the land use models, and you get a huge difference in the grassland areas. I mean, already imagine what the difference there is. Without any further iteration, you can already explore how does that affect other things. So there's already quite some richness. Yeah.
Great.
Thank you.
Thank you, Herman. Yeah, thank you. All right. Not least, Kevin.
Right.
There we go.
I know I'm the only thing standing between you and lunch, so I'm gonna try to go quick. Moving from the global scale to the regional scale in New York State. So this is I'm going to present a participatory modeling approach for really incorporating management decision-making into models in conjunction with farmers. So the goal of our project is to protect New York City's water supply into the future. It is very high quality water. A lot of it stems from this area that is our focus area, which is predominated by agriculture, small beef and dairy farms. But crucially, the water that comes to New York City is unfiltered. And so we want to make sure that water quality stays high as it comes from these agricultural areas in the watershed, so that the city doesn't need to invest in filtration systems. So they're very heavily invested in keeping the agriculture the water that comes from agriculture very clean. So we're working with the city and with a group of farmers on this project. They have a very interesting kind of approach where the city pays these farmers incentive payments for best management practices. So incentivizing farmers to take a series of practices that protect water quality while they're dealing with manure and tillage, etc. And so the question they want answered is, are these management practices going to be fit for future climate conditions to maintain water quality into the future? So, introduction to best management practices. There's many practices, and what's complicated here, especially when trying to represent management decision-making, is that these practices are linked together as a chain of interconnected practices. So we have nutrient management planning, which is essentially where, how, and when to spread manure on fields. You have things like prescribed grazing, rotational grazing, moving animals around, cover crops, different types of tillage practices, where to install riparian buffers, how big, and what types of even barn and barnyard infrastructure farmers need. And if there's constraints in the ability of a farmer to successfully implement, one component of these practices, it actually has this ripple effect to these other decisions in management. And so it's quite a complex system to manage or to try to model. They've been seeing increasing amounts of extreme weather in the Catskills. We've had hurricanes and lots of extreme rain events. But in addition, we've recently had New York City this past fall issued its first drought warning in the past 20 years. So drought may be an issue as well, which is a new cause for concern. Okay, so now we're trying to, these agricultural systems, it's a moving target to represent them. So we are trying to represent the management here and also represent changes in land use. I'm looking at Roberto because he's more responsible for that part of things. And all of all those questions you can take to him. And all of these things contribute obviously to water quality and are influenced by climate change and lots of interactions along the way. One way we're doing this in our scenario development is The land use change, as I mentioned, is co-developed with stakeholders via this process of representative agricultural pathways. I'll talk a little bit about that. Again, Roberto is the expert. And I'm going to talk a little bit more about focus groups, which are led by a colleague, Malgosia Medejewicz. Sorry, Malgosia, if you're listening, I butchered your name, who's a social scientist in our group. So, you know, lots of people that we have to talk to in various rooms over a number of years. For the focus groups, we're talking to farmers, also lots of ag extension agents. And the process is kind of, you know, it's iterative. So the first focus groups, we're learning about the context. What do we need to be aware of when we develop our first model? Then we take our models to the farmers, the stakeholders. Are we getting this right? After they say, yes, you're representing these management decisions right, and we get the kind of blessing to go ahead, we run our models, interpret the model results with the farmers and other stakeholders, and then collaborate on developing recommendations. So this is results from just trying to figure out all the different constraints to implementing management practices for farmers. And, you know, I'm not going to get into this crazy mental model, but you can see there's so many interactions that we need to be aware of. We're not going to represent all of this, but we're going to try to, with the stakeholders, simplify some of the key processes that we can bring into our models to represent a range of implementation scenarios. So this is how we're modeling kind of management in our project. We have a baseline implementation scenario. So this is average implementation of these management practices on the average farm to the best that we can do this across the watershed. And then we have a resource constrained implementation. So this could be time, labor, capital. How does that affect a farmer's ability to implement existing BMPs? So, you know, creating scenarios around that without new BMPs being adopted. And then non-constrained implementation, if farmers had all the labor, all the time, all the money, how would they implement these BMPs? So we're trying to capture really the range of the water quality response to management implementation, all the way from very constrained to non-constrained whatsoever. So each scenario has an explicit implementation narrative. So we are writing out all of the assumptions in the chain of events that happens under these different implementation scenarios. And crucially, those narratives are consistent across practices. So we're representing those ripple effects. So if there's in a management scenario, if there's an issue with manure spreading, it feeds back onto manure storage systems, for example. So it's consistent. Also we have to capture differences not only between beef and dairy farms, but between lactating cows, how they're managed, and beef herds and grazing heifers. So this is the type of thing we're bringing to the farmers. This is like a parameter table. We're running the SWOT model, hydrological model, and we're trying to get actual quantitative feedback from farmers. Before we do that, we take them through kind of a narrative scenario. So, you know, for manure deposition in a resource-constrained environment, if you're managing lactating cows, let's say there's a reduced grazing management capacity, you have less ability to manage cows in the fields, they have to spend more time in the barnyards, increased barnyard time places additional demands on manure storage systems, limited equipment and labor availability restricts the amount that you can spread, therefore you have to spread higher manure volumes, which when we run this through our models, if they're spreading during rain events, higher manure volumes, you see the water quality impact. But the SWOT model can actually take in a lot of these parameters. I'm not going to go through it, but you know, we can take in everything from grazing days, but you know, how much they're spreading per field during which part of the season, on cornfields versus hay fields, how much is injected versus applied on the surface. We're bringing these to the farmers and getting feedback on quantitative parameters. And yeah, so this is the process of doing that. So that's creating kind of the management scenarios. We're also doing the land use change scenarios. This is the RAPS process. You can't see Roberto in here leading it, but he's responsible for us doing all of this stuff. So basically, he's working with stakeholders to develop what the agricultural land use mix might look like in the future. So perhaps there's a strengthening of dairy farms. So there's an increase in dairy farms. currently they're declining, but perhaps new policies will bolster dairy farming, or there's a transition to beef farming. So there's going to be a different mix of beef and dairy in the region, also a different mix of farm size. Could be bigger, more efficient dairies versus smaller dairies. And we have to try to capture these assumptions as we generate our land use scenarios for the future. Okay, so what can we do with all these scenarios? So we have current agricultural land use. Let's say we're just looking at the current climate. We can look at the different BMP implementation scenarios and just ask how does BMP implementation impact water quality at the basin level under current conditions? We can then go with our current agricultural land use, but look at the different climate change scenarios we're running, SSP 126 and 370. How does climate change impact water quality under current land use and management? So keeping land use and management constant and just looking at the climate impact. We can obviously then do this for all of the other implementation scenarios and say how may climate change impact water quality with different levels of BMP implementation. So this is looking in the future, different levels of BMP implementation times climate change. Then, of course, we're bringing in Roberto and looking at land use scenarios. So, for example, here we're saying how does this whole mix change under different mixes of land use in the region? So this is next steps here. We actually now are representing all these different linked practices. We have the ability to turn them on and off and see which are most sensitive in the modeling to water quality outcomes. And we could also, we're looking to do some spatial prioritization of where in the watershed the BMP prioritization is the most effective. So key takeaways. One thing that I've learned is we can actually, this seems complicated, but if you sit down in a room with farmers, you can actually distill modeling into sets of assumptions that they will understand. And hopefully that not only makes the modeling better, but it builds trust, will help the end users actually use the information because they're invested in this process. Another thing that I've learned is that modeling complex chains of management decisions is possible, but you really need the farmers there because there's so many assumptions and it could go wrong very easily. And the process of gathering stakeholders to envision plausible futures, what Roberto does with RAPS on its own, I think has a power that's a little bit hard to describe just in the paper. You're gathering groups of people that don't usually sit together to think in a structured way about the future of their community. And so I just want to advocate for that as a good on its own with benefits that we don't necessarily maybe comprehend. That's it. Thank you.
Great. Thank you.
So I don't want to limit the discussion, but if you want to do questions, maybe just one question. I don't. So lunch is going.
Yes.
So you guys don't want to miss lunch, and there is going to be a meeting here over lunch. But I don't know.
John. You can stay. Yeah, you can stay. Maybe I guess what I'm hearing is we should probably adjourn.
Yes,
please direct your questions to Kevin and appropriately Roberto and some, where that's. But thank you all very much for sticking around for the presentations.
Thank you, teacher.
Well, we'll see. High condition might change. Hopefully.
Yeah. You were right. Yeah.
Like yesterday, we got stuck at some point with the
Yeah, the secret. I mean, well, now I don't know how to get this. So we, by mistake, touched the screen. And it's okay, but it's not.
That's okay. It's okay.
Okay, sorry. Yeah. Yeah, I like it. You need to.